about Prikry type sequences, a composition of interconnected results. Now, Carl Prikry long time told me that he dropped all the checks and accents, and also Stevo Todoroshevich says he's dropped all those. I'm see that they're resurrected here.
Yes, thank you. Yes, I have a little macro. I just have to write \Prikry and all the accents appear automatically. Yeah, let me thank the the organizers for inviting me. Also, let me thank the speakers for giving such interesting talks. And also thanks to Adrian for clarifying what dress code smart casual means. Okay, so when I got invited here, I thought I would try to talk about something related to Mathias' work that I have been interested in for a long time. And so, I don't know, the first part of my talk is going to be kind of brainstorming what it is that I find most fascinating about Prikry forcing and Prikry type forcings. So let me just maybe get started. So I think we all know this forcing, but just to recap. So kappa is a measurable cardinal, and we fix a normal ultrafilter on kappa, call it mu. And the conditions in Prikry forcing are pairs, where the first component is a finite subset of kappa, and the second component is a measure one set, so that so the first part is called the stem, right? So the stem is below the rest of the condition, so S is contained in the minimum of T. And the ordering is that you basically can extend a condition by lengthening the stem and shrinking the second part of the condition. So lengthening the stem by things that are in the measure one part of the weaker condition. So in a picture, so this is kappa. You have a finite stem, so finitely many points, and then you have a reservoir of measure one many possible extensions of that stem. I think the first time I saw Prikry forcing described, that's a long time ago, Peter Köpke gave a talk on it, and he always described these as looking like trees, so that's why the stem is brown and what comes above it is green. So, okay. So to extend the condition, you can pick some of the formerly green points, right? And then you have to shrink a little bit to make sure that the stem is below the minimum. And then you can shrink the measure one set a little bit, but it still has to be measure one. Right? Okay. And so one basic thing is that when you do Prikry forcing, you can recover the entire filter from just what you get when you union up the first coordinates that occur in conditions in the filter. So it's determined by this omega sequence. And this sequence is cofinal in kappa, and Prikry forcing doesn't add any bounded subsets of kappa, and it's kappa plus CC. Okay, so it changes the cofinality of kappa to omega, and it preserves cardinals. Okay, so the main result due to Adrian Mathias is this characterization of when a sequence of order type omega is Prikry generic. So such a subset C of kappa is generic for Prikry forcing if and only if for every measure one set C is almost contained in A. Okay. And okay, so basically that just means that the sequence basically is belongs to every typical set in the ground model, and there are characterizations, you know, like for random reals there is a similar thing that a real is random if it doesn't belong to a set that's coded by has a Borel code in the ground model that has measure 0, and for Cohen reals you have something like that too. So it's in that vein. Okay, so I'm heading for a so the way I see it, this characterization of Prikry genericity kind of opens up a connection between Prikry forcing and iterated ultrapowers, which I'm heading for. Okay, so I will just write J goes from V to M with this little index mu to indicate that J is the ultrapower embedding from V into M, and M is the ultrapower by mu. Okay, and of course I take mu to be M to be transitive. Okay, so of course the critical point of this embedding is kappa. Kappa is represented by the identity function because the measure is normal, and so X belongs, a subset of kappa belongs to mu if kappa is in the image of X. Okay, so now I want to iterate this. So we start with V. Sorry, this should be V comma mu, not U. I knew I was going to miss one of those U's. You will see later why it has to be mu here and not U. So anyway, so then we have this embedding from M0, which is V, to its ultrapower. Mu1 is going to be the image of, again, mu0. And so you go on like this, and it will be sufficient to do this countably many times for now. Okay, so we have this linear system of models and embeddings. These embeddings just result from composing the ultrapower embeddings. And after omega many steps, we have a length omega iteration, and it's a directed system. We can form the direct limit. It's going to be well-founded, and so I will denote the direct limit embeddings Jn omega. Okay, so then we have, let's write kappa n for the nth critical point. That's the same as the image of the original measurable cardinal under the embedding into the nth model. And the kappa n sequence is the critical sequence of mu again. Okay, so so the critical sequence is then cofinal in kappa omega, and kappa omega, of course, by elementarity, is measurable from the viewpoint of m omega. So so the critical sequence doesn't belong to m omega. Okay, so if I write p index mu for Prikry forcing with respect to mu, then the connection between this iterated ultrapower construction and Prikry forcing is, as probably many of you know, but I think it's an intrinsically beautiful connection, that the critical sequence is Prikry generic over m omega in the sense of the image of Prikry forcing. Yeah. So basically just Prikry forcing in the sense of mu omega, if you will. I think this is due to Solovey, but maybe you know better. In any case, knowing the characterization, it's very easy to see. So I just want to illustrate this. It's a very simple proof. So so by the Mathias characterization of Prikry genericity, we just have to show that a tail of the critical sequence belongs to any measure 1 set. So if we take x in mu omega, then what we can do is, okay, this x occurs in the direct limit, so it has a pre-image somewhere, right? So let's say it has a pre-image in mn, and let's call x bar, let x bar be the pre-image. Then from that point on, the kappa m's are always going to be in, and the reason is since x was in mu omega, this x bar is going to be in mu sub n, right? And by one of the facts on ultrapowers by normal measures, that means that kappa n is an element of the image one step later. So now we can apply Jn plus 1 omega on both sides. That won't move kappa n, and it will move x bar back to x. So that shows that kappa n is in x. Okay, so this works as soon as x is in the range of pi n omega. So this happens on a tail, and that shows that the critical sequence is Prikry generic.
I also think that argument is into
this.
No, but it's Kuhn's argument plus my characterization.
Okay, yes, I guess that's true, yes. So in any case, I think what makes this proof work is this characterization, and the rest is very easy. Again, this was the characterization, right? In fact, so this is this starts out with a measure one set and concludes that then the Prikry sequence is almost contained in it, but it's actually you can go both ways. So if C is a Prikry sequence, then for every A, a subset of kappa, A is in U if and only if C is almost contained in A. Okay, so one direction there is already done, right? The other direction is very obvious. So if C is almost contained in A and A was not in U, then the complement would be in U. But then that would mean that a tail of the sequence would have to be contained in the complement of A, and so that can't be. So so this means that if you have a Prikry sequence, then the measure for which it is Prikry generic can be defined in the Prikry extension from the power set of kappa in the sense of V and the Prikry sequence. Yeah. Okay, so now I want to see what happens if you iterate more than omega many times. So this is something that will turn out not to work. But of course you can iterate. You can go on past omega and form linear iterations of just larger length. And so the system also comes with a critical sequence, and so the naive question would be, is this sequence going to be generic over the limit model, right? And so, for example, if kappa is measurable, but it's not, there's no smaller measurable cardinal in any set forcing extension, let's just work with such a kappa. Okay, we can always get some kappa like that if there's a measurable cardinal. Then it's not hard to see that the critical sequence cannot be generic over n lambda. Not even the first omega length sequence can be generic, and the reason is just that mu omega would also be added by the forcing that adds the sequence, because from the sequence you can define the measure. But then you can see fairly easily that this mu omega still would be a measure on kappa omega. And so that would mean that m lambda would have a forcing extension where there is a smaller measurable cardinal than kappa lambda, which we excluded, right? By elementarity, there is no such forcing extension. So this the omega length sequence of measures critical sequence cannot be added by any forcing over m lambda as soon as lambda is greater than omega. Okay, so this is nothing deep; it's just an observation. And so the problem seems to occur, so to speak, as soon as you hit one measure more than omega many times. So so the simplest way to avoid that, I guess, would be to switch to a larger measure after omega many steps. All right. And so so this leads to a generalization of Prikry forcing that I looked at a while ago, actually a pretty long time ago. And but okay, let me just show you the setup. So the starting point here is a discrete set of measurable cardinals. So no limit points of the set are in the set itself, so no measurable limits of measurable cardinals in there. And alpha, let's say, is the order type of D, and kappa gamma is the enumeration. And let's fix U sub gamma, a normal ultrafilter on kappa gamma. And let's fix the sequence eta gamma of ordinals between 1 and omega, omega inclusive. So the idea is basically, okay, so once I have defined the forcing, I will produce an iteration that is supposed to have similar properties as with Prikry forcing. The eta gammas basically tell you how many times you will hit U gamma in the iteration. And from the forcing point of view, the eta gamma tells you how many points below kappa gamma you want to add. Okay, so the idea is I'm not so much interested in collapsing cofinalities or anything. So for example, if eta gamma was always 1, that would mean I would add 1 point below every measurable cardinal, and it will turn out in that case I wouldn't collapse anything, no cardinals, no cofinalities, but it will still be a new sequence with some combinatorial properties. Okay, and if eta gamma is omega, I will end up collapsing. So okay, so the conditions are again pairs s comma t of functions where the domain of S is a finite subset of kappa, and so that and the domain of T consists of those gamma where the cardinality of S gamma is less than eta gamma. So where basically I haven't already specified the entire sequence at the gamma's coordinate, and T of gamma, if defined, is in U gamma, and for gamma in the domain of the S, S of gamma is a finite subset of kappa gamma of size less than 1 plus eta gamma. So, and S of gamma is below the minimum of T of gamma, and also S of gamma is greater than all the smaller measurables, right? The supremum below is always bounded in the next measurable, so this can always be arranged. And the ordering is basically component-wise like Prikry forcing. So S prime T prime is longer or stronger than ST if, okay, the first component is extended by points in the specified reservoir at coordinate gamma, and if S prime of gamma is less than eta gamma, i.e. that means that T prime of gamma is still defined, then T prime of gamma has to be contained in T of gamma. Okay. All right. So the way you can kind of remember it quickly is kind of like a product of Prikry forcings where we take finite support in the first coordinate and full support in the second coordinate. And we have some added flexibility via these eta gammas because I'm not always adding omega sequences. Okay. Okay, so let's see, I drew a picture for that too. So this time we have a bunch of trees, and they are growing on a very steep hill, right? So all the points here are above where the previous tree ends, and so to extend, you basically can do the same thing as in Prikry forcing. You can just make the stems a little longer by points that were formerly green. You can shrink the green part a little bit, and in some cases here, for example, the eta 2, I guess, would be 5. Right, so if once I have a finite sequence of length eta gamma, I don't have to say how I could extend it because I won't be able to extend it anyway. So those trees have lost their leaves, so to speak, right? Okay, so that's what this looks like. Okay, and in this situation, the generic filter corresponds to, again, a function with domain alpha, and for every gamma less than alpha, G of gamma is a subset of eta gamma of order type, subset of kappa gamma of order type eta gamma. Okay, and if eta gamma is omega, then G of gamma is going to be cofinal in kappa gamma. So those guys will be collapsed to omega, and so you can show that this forcing changes the cofinality of an ordinal lambda if that cofinality is equal to kappa gamma for some gamma where eta gamma is omega. Otherwise, it doesn't change the cofinality. Okay. And it preserves all cardinals. Okay, so then I showed a generalization maybe of Mathias' criterion for Prikry forcing, and it reads as follows. So if you have a function f with domain alpha, then that is generic for this forcing if and only if for every gamma less than alpha, f of gamma is a subset of kappa gamma of order type eta gamma. And I guess you also have to demand that that the minimum of f of gamma is greater than the supremum of the smaller kappa gamma bars. I forgot to say that here. But anyway, so the point is that you have to have that for every sequence x gamma from the ground model, so to speak, so that x gamma is always in u gamma. Altogether, if you union up how many times f of gamma is outside of x gamma, it's finite. So not only for every coordinate it's finite, but altogether, simultaneously. Okay, so and for this proof, it's kind of important that the set of measurables is discrete, because it allows you, basically you do a kind of a product analysis all the time. You split the forcing in a lower and an upper part. The lower part is then smaller than the closure of all the later measurable cardinals, so you can kind of simultaneously homogenize and do things like this, and work your way up level by level. And it's also kind of like by induction on the length of the sequence you show this. So it's so this is one of the first theorems I proved, I think. And yeah, I found it pretty tricky, but it relies on, it's a similar argument as for Prikry forcing. Okay, and just to simplify notation a little bit, let me just focus on one special case, and that's the one where eta gamma is 1 always. Okay, so below every measurable, we only add 1 point. And so this is similar to what Magidor calls a diagonal Prikry forcing, I think, right? There we would have an omega sequence of measurable cardinals, and below every one of them you add 1 point. Here, the sequence may be longer, but it's so it's I guess a generalization of that. Okay, so we always just add 1 point below every measurable. Okay, so now we want to imitate this forcing by an iteration. So the idea is, again, I want to iterate in such a way that the sequence of critical points is going to be generic for that forcing over the limit model. Okay, so we start with V. And the question is, of course, what are we going to do at the successor step? Okay, so if we have defined Mi already, then I'm going to apply Wi, where Wi is pi 0 I of the whole sequence of that you have in the ground model at the ith coordinate. Okay, so you take the ith ultrafilter in the current model, right? You take the current model's version, so to speak, of the U sequence, and you take the ith model element of that sequence. So this is kind of an so what happens here is interesting when I guess the order type of that sequence is greater than the minimum of the measurable cardinals that you have there, because then you will stretch it out, and you will apply measures that don't have a pre-image in the ground model when you do this. Okay, and the really interesting case it will be that alpha, the order type, will be equal to the supremum of these measurable cardinals. So there is no requirement that alpha is small or something like that.
So first you apply pi 0 I to the sequence and then take the ith component?
Yes. Okay. Yeah. During the iteration, the length of U may increase, right? Yeah. So I work my way up the current version of the sequence always. Yeah. Okay. Then, of course, we piece everything together, just compose the iteration embeddings to get all the embeddings, and at limit lambda we take the direct limit and take everything to be transitive. Okay, as I said, if alpha is larger than or equal to kappa 0, then there will be ultrafilters applied here that don't have a pre-image. Okay, and this will terminate at some point, and at that point we will have that I is equal to pi 0 I of alpha. Right. Okay, so let's call M alpha tilde the last model in this iteration, and let's write lambda I for pi 0 I of the kappa sequence at component I. Right. So lambda I is going to be the critical point of pi I plus 1. And so the lambda sequence is now the critical sequence. Right. And so it turns then out that the sequence is M alpha tilde generic for the image of the forcing. Okay. And so this, okay, you can do this imitation iteration also in the more general case where you have different eta gammas. Then basically eta gamma will tell you how many times do you have to iterate the current ultrafilter before you move to the next one. It's just a little more tedious to write it down. And the same result holds. Okay, I guess I maybe should have said this about Prikry forcing also, namely this maximality property. So if you have a generic sequence for this generalized Prikry forcing and f is also generic and it belongs to V of G, then f is almost contained in G. So the generic is, so to speak, kind of maximal in its forcing extension. So this is something that is also true of Prikry sequences, and it's very easy. I mean, it's not hard to show it, show this property using the fact that you can imitate the forcing by iterating. So this is, so the way I see the connection between all of these things is, okay, you have the forcing and you have a characterization theorem like the Mathias criterion, then you can use that to show that you can iterate and the critical sequence is going to be generic, and knowing this you can show maximality. So all of this is kind of connected. Okay, so oh yeah, and in the special case that we were interested in, so this holds in general, right? But in the special case where you only add 1 point at every coordinate, you know, below every measurable, but then this basically means that the generic is unique up to finite changes. Okay, the unique generic in the forcing extension. Okay. So now I want to move to Magidor forcing and do the same thing. Okay. So with Magidor forcing, you start with a measurable cardinal that carries a sequence of normal ultrafilters, which are increasing in the Mitchell order, and that sequence is of length alpha. And this alpha is less than kappa. Okay, so in the previous example, alpha was allowed to be large. Here it has to be small. Okay, so now it gets a little combinatorial, but okay, so meaning, so what does it mean that these U gammas are increasing in the Mitchell order? Right, it just means if gamma is less than delta, then U gamma is in the ultrapower of the universe by U delta. But that means that there is a function that represents U gamma in that ultrapower, right? And that function is going to be F delta gamma. Okay, so we just fix functions that do this. So right, so this F delta gamma represents U gamma in the ultrapower by U delta. And so this is the way to write this. And then, because of normality considerations, there is a lot of reflection going on with the system of F gamma deltas. So if you fix a gamma less than alpha and you let B sub gamma be the set of inaccessible delta less than kappa, such that basically at that delta the sequence F gamma mu of delta and F gamma nu of delta and so on, so you just plug in this delta fix gamma. This is going to be a Mitchell order increasing sequence of normal ultrafilters. And moreover, the representing functions are given by restrictions of the original functions. Okay, so this is going to be B sub gamma. So that is a measure 1 set. Okay, so this is an observation of Magidor, and it allows you to define Magidor forcing like this. So again, conditions are pairs of functions. The first component is a finite. The first component is a function whose domain is a finite subset of alpha, and the second component will be defined at all the points where the first component is not defined, and these G of gammas will increase, and they will always be in the B sub gammas. G of gamma is always going to be in B sub gamma, so we have reflection. And the G of gammas are always going to be measure 1 sets, but to see what ultrafilter they're going to be measure 1 for is a little tricky. So if you are at gamma, then you look to the right. What is the next point in the domain of little g, if there is one? Okay. Let's say that one is theta. Well, then we require that g of gamma is in f theta gamma of g of theta. So g of theta is a measurable cardinal, and f theta gamma is basically the gammath ultrafilter of on that measurable cardinal that we're interested in. So that's where g of gamma, capital G of gamma, has to be. And if there is no point to the right of gamma in the domain of little g, then big G of gamma is going to be in U gamma. Okay, so that's where the sequence that we started with. Okay, and then also so the G of deltas always are going to be above all the previous little g of gammas. Okay, so the extension is exactly as you would expect. Like the first components can be extended, and when you extend, you have to extend by picking a point in the measure 1 set that is corresponding to that point, and you can always shrink the second component. Okay, so here's a picture. So the first component kind of looks like this. Okay, so let's see. So this stretch here is alpha, kappa goes up. Okay, so the picture is wrong because alpha should be smaller than kappa, right? But that's the layout. Okay, so the stem is now going to be these scattered points. It doesn't grow vertically anymore, so to speak, right? So these are the little g of gammas, right? Finitely many points. Each of these points is going to be a measurable cardinal. And say g of gamma 1 is going to be in b sub gamma 1. Right, so we have this canonical sequence of normal ultrafilters increasing in the Mitchell order going up here because I'm in B sub gamma. So for every measurable cardinal there we have the sequence. And the second component, the green part, is just going to pick measure 1 sets from the corresponding normal ultrafilters. Okay, and so to speak here, you look to the right, what's the next point in the domain of little g? You look at its measurable cardinal. Well, that's where the measure 1 sets have to be. Okay, so that's how that works. And after the last one, there is nothing to the right, right? So you just pick the measure 1 sets in the U sub deltas that you started. Okay, and now, so this is what a condition looks like. And when you extend, you can, let's just extend by adding 1 point to little g, right? So you can choose a coordinate where you haven't specified little g yet. You turn a formerly green point into a brown point. Then you have to see also, okay, so this guy is going to again be a measurable cardinal, and then you cut off everything that you had before and also everything you had above, but you cut it off below. Okay, and then you can shrink the measure 1 sets in addition a little bit. Okay, so that's how you extend Magidor sequences. Okay, so what are the properties? The generic filter corresponds to a function from alpha to kappa called a Magidor sequence. It's monotonic, it's continuous and cofinal in kappa, and it preserves cardinals. So it changes the cofinality of kappa to alpha. Let's say alpha was regular, then it would be exactly that. And it preserves cardinals. Okay, and so this is a theorem, I don't know, I think Moti said he knew it and some other people knew it too. I couldn't find it anywhere, so I sat down and just proved it. Basically, it's a characterization of what Magidor sequences, you know, how do I recognize a Magidor sequence, okay? And it's, okay, so let's see, a strictly increasing sequence C, so that C of gamma is always in B sub gamma. It has to be greater than alpha always, right? It's going to be generic if, okay, so now there are two conditions. The first condition is if you take any sequence x that's in the ground model, so that x of gamma is always in U gamma. So the U gammas are the ultrafilters that you had on kappa, right? Then a tail of the C of gamma sequence has, on a tail, the C of psi has to be an x psi, okay? And so this has to hold basically at the original sequence on kappa. but then also, whenever you take a limit ordinal beta, let's say, it's only interesting for limit ordinals. So the C of beta is going to be a measurable cardinal, a smaller measurable cardinal, right? And it comes with a length beta sequence of normal measures going up to there. So whenever you take a sequence of x gammas that always are in the actual normal ultrafilter responsible for this C of beta, this is f beta gamma of C of beta, then on a tail below this beta, C of psi always has to be in x of psi. So this has to hold basically at every limit ordinal. Okay. So it's kind of it looks kind of tedious because of all these indices, but it's actually not so surprising. So so it's the natural thing you would expect, like or you would hope anyway. So but it's combinatorially a little tedious to show it. Anyway, again, so we have this characterization of Magidor sequences. So now we should be able to iterate and produce a critical sequence that is generic for it, right? And so what you do is you start with V, and okay, supposing you have already defined the beta first steps, then let's just look at the image under J0 beta of the original sequence of measures, U, and apply the betas of those to n beta, okay, to get n beta plus 1. And then at limit stages, just take direct limits. Here, by the way, since we always, all these measures, that we start out with, so the critical point of this whole embedding is going to be kappa, right? So the length of the U sequence is not going to be increased. So this U beta sub beta is the same as just J0 beta of U beta. So every ultrafilter I apply here has a pre-image in the original, in the ground model. So in a way, it's simpler a little bit than in the other case. Okay, and so this sequence is generic over the limit model. So the sequence of critical points is again generic over the limit model, and this was shown by Durannois in 1984, and he proved it without knowing the characterization of Prikry genericity. He just showed it directly, but he showed it for a tree version of Magidor forcing, and I don't know, I tried to read his paper and I just didn't understand it. So he has this way of representing arbitrary iterated ultrapowers as single ultrapowers, and it's very hard to understand to me, at least. So I just sat down and proved the characterization theorem and then showed that this sequence satisfies it. Okay, so but now, as I said before, once you have the genericity of the critical sequence, then usually this makes it possible to show some kind of maximality result. Okay, and so here it reads like this: if C is generic over M for this Magidor forcing, and D and V of C is also generic, then for all but finitely many gamma, they have to be equal. These two sequences. So it's the uniqueness modulo finite changes, and also for at limits they have to coincide, because otherwise you would have, because they are club, so otherwise you would have to change infinitely much. So, and there is a lot of other stuff that I then also showed, but I don't want to go into this. So this is one of these things. So if you add a Magidor sequence, it doesn't add a Prikry sequence. So it's not a generalization of Prikry forcing. It's something totally different. But it has shares many properties with Prikry forcing. So okay. So the way I see it, we have now 3 examples of forcings where you have very similar properties, and so you can do this imitation iteration that produces a critical sequence that's generic over the limit model for that forcing. Yeah. And I would like, I mean, it's just, okay, I kind of would like to look at it from a different angle that maybe explains to a certain degree why you have these critical sequences be generic. Of course, okay, we know the deeper reason because we have gone through the proofs, right? So this is the reason, but I think there's a scenario that explains it in a different way, and that's the context of Boolean ultrapowers. So let me just give a brief outline here. So if you have you start with a Boolean algebra B, and an ultrafilter on B, usually countably complete, or at least we want the Boolean ultrapower to be well-founded later on. So for B names sigma and tau, we identify them if the Boolean value that they are equal is in the ultrafilter that you chose, and sigma sub u, that's the equivalence class. Then you define a pseudo epsilon relation on the equivalence classes by saying that sigma u e tau u, if sigma element tau, the Boolean value of that is in u. And then you can look at the model that you get, VB mod u. I'm following Hampkins notation here. There's a paper by Hampkins and Siebold where they explore all of, a lot of the construction of Boolean ultrapowers. And so this VB mod u has a submodel that consists only of the equivalence classes of such names where the Boolean value that sigma is in V check is in u. Okay, so these equivalence classes are what they call V check sub u. And there is an elementary embedding from V to V check sub u. And that is the canonical embedding setting x to the equivalence class of its name. Okay. And so V check sub u, that's the Boolean ultrapower of V by u, and J is the Boolean ultrapower embedding. Okay, so as I said, I want the Boolean ultrapower to be well-founded usually, and so I just take V check u and VB mod u to be transitive. And so then, the equivalence class of the canonical name for the generic object, G dot, so the equivalence class of that thing is in VB mod u, right, because it's just a name. And it turns out that this, we call this G, this is V check u generic, okay? And in fact, the VB mod u model is the generic extension of V check sub u by G. Okay. So the picture looks like this. We have J from V into V check u, which is contained in its forcing extension, which is just the Boolean model. And it's easy to see that when you pull back the generic ultrafilter, you get u. Okay, so with Prikry forcing, for example, we had an embedding from V into m omega, and m omega was contained in its forcing extension by the critical sequence, right? And so the question is not far-fetched whether this embedding can be realized as a Boolean ultrapower. Right? So that's what I mean. In a way, this would explain why there is this object, why there is a generic around. Okay, so the first question, what Boolean algebra should be used? Well, the critical sequence is generic for Prikry forcing, so let's take B to be the Boolean algebra of Prikry forcing. And what ultrafilter should be used? Well, by what I said, it has to be the pullback of the generic, right? So let's take U to be that, and then it turns out that this works. So this is not hard to see because so this following theorem basically tells us that you have taken a Boolean ultrapower if you can describe everything. So if you have a generic filter around over the target model, so that you can write every element of your model as J of F of B sub A, where A is the maximal anti-chain in B, and B sub A is the unique element in A intersect G, in J of A intersect B, intersect G, yeah. Oh, sorry, F in our case, yeah. Okay, so we have basically the B sub A's, these are we have to show that these generate the model. Okay, so in the case of iterated ultrapowers all by the same ultrafilter, that's not hard to do. So let's apply this theorem with B being the Boolean algebra of Prikry forcing, J is the limit embedding, B check is omega, is m omega, and F is G. So G that's the generic generated by the critical sequence. Okay, that's generic over m omega. So if we take an element x in M omega, we know already this has the form J0 omega of f of a finite chunk of the critical points, right? So let's say, so this is a length n sequence now, okay? Okay, let me skip some details. We take the maximal anti-chain consisting of the conditions in Prikry forcing that specify n many points in the first coordinate, and the second coordinate is the maximum measure one set you could put on there. Okay, so finitely many points, length n many points, and then just kappa minus the maximum of this. So, and the first coordinate varies. So this is the maximal anti-chain, and it's basically the elements of this anti-chain are determined by the first component, which is just length n increasing sequences, right? So this is kind of, it's clear then that if we just define, we had this f, if we just define f star of s like f, but just depending on the first component of the condition, we will get that the original x, which was J0 omega of little f of these kappas, is going to be J0 omega of f star of the b sub an, because b sub an will have in its first component kappa 0, kappa 1, kappa 2, up to kappa n minus 1, and then everything above that. Okay, so it's very easy. Okay, so then these are the same, right? Sorry, this went too fast maybe. So we have this iterated ultrapower. It can be described by a single Boolean ultrapower by the correct ultrafilter U on Prikry forcing. Okay, so the obvious question, does this work for generalized Prikry forcing and for Magidor forcing? And the theorem, so we're currently working on this, Joel Hampkins and I. The theorem is yes. Okay. And this is fairly easy to see in Magidor forcing. Basically do the same trick. And it's pretty tricky in the case of generalized Prikry forcing if the forcing is long, meaning that the order type of this discrete set of measurables is greater than kappa 0. It gets pretty tricky, but you can show it. So, okay, so so the Boolean ultrapowers generalize, explain maybe the existence of a generic, right? Because every Boolean ultrapower comes with a generic or the target model. So, or at least it's another angle to look at it. And okay, so now I want to move to another, I think, really puzzling phenomenon about all of this, which is what we call the Bukowski-de-Lannoy phenomenon. So, for Prikry forcing, for example, we had this immutation iteration. The critical sequence is generic over the limit model, and it can be also described as VB mod U, but it can also be described, the forcing extension can be described as the intersection of all the MNs. Okay, so we get the forcing extension of the limit model by the critical sequence by intersecting all the finite iterates. And so the question that arises when you look at it from the angle of Boolean ultrapowers is whether this is maybe a phenomenon that holds in general of Boolean ultrapowers. So the left-hand side, m omega of kappa, can be described, of course, as VB mod U, right? So the question is, what should go on the right-hand side, right? And so here, you know, the point is that you can describe Boolean ultrapowers as direct limits of certain systems of embeddings, and they work as follows. So if you take a maximal anti-chain in B, then you can define an ultrafilter on the power set of A by taking all the subsets of A whose supremum is in U. Okay, so this is just an ultrafilter on a set now. And you can take the ultrapower of V by that, and let's call the model you get M sub A. And usually it will be well founded in the cases that we are interested in. Now if you have anti-chains A and B, then B refines A if every element of B lies below an element of A. Okay, so and it turns out then that okay, so the maximal anti-chains are directed under refinement, and whenever B refines A, then there's a canonical embedding from MA to MB. And so these MAs with their embeddings form a directed system, and when you take the direct limit, you get V check U. Okay, so this was all worked out by Hankins and Siebold in this paper, and so now we have something that we could write on the right-hand side there, right? So again, for Prikry forcing, we had this situation: m omega of kappa is the intersection of the mn's. So the left-hand side is just VB mod U. The right-hand side, could it be intersection over all maximal antichains A of n sub A? That would be the question. Right? So this would be wonderful, but we don't know if it's always true. So that's what we're currently working on. But let me just give you some results in this direction here. Okay, so if you look at the inclusion m omega adjoint kappa is contained in this intersection of the mn's, what's crucial in the usual argument is that in mn you can see the tail of the iteration, right? In mn you have un, you can iterate that, and so you get everything up leading up to m omega. That's why m omega is in there. That's why the tail of the generic sequence is of the critical sequence is in mn. But then there are only finitely many points missing below, so the whole sequence is in mn. This goes for every n, so you're done with this inclusion, right? Okay, so so in order to argue like this, we would like to know that this, so translated to the Boolean ultrapower situation, we would like to know that pi a infinity is in MA for every a. Okay, so the question is, how could you do this in general? And so what you can do is pull back the generic over V check U pointwise under pi a infinity, and call this G sub A. Okay, so if you form the ultrapower in MA with respect to pi 0 A of the Boolean algebra that you started with, modulo this pullback of the generic modulo GA, then you get VB mod U. Okay, so assuming well-foundedness, they are the same. And actually the embedding pi a infinity is the Boolean ultrapower embedding by G sub A. Okay, and the generic that you get from forming this ultrapower is the same as the original G. Okay, so in the transitive case, the VB mod U you started with is the same as this model. When you go to MA, move the Boolean algebra as you have to move it, and form the ultrapower with respect to the pullback of G. Okay, so this is just a calculation. I mean, it's yeah, you just calculate that. So the question is, okay, so in order to conclude that we have VB mod U contained in the intersection of all the MAs, we wanted pi a infinity and VB mod U to be definable in MA. Okay, but this is equivalent to assuming that G sub A is in MA. Right? If G sub A is in MA, then we just saw that we can define both of these things because they are just the Boolean ultrapower embedding and Boolean ultrapower construction with respect to G sub A. And vice versa, if we have this desired inclusion and pi a infinity is in there, then we can calculate what the pullback of G is. So G sub A has to be in MA. Okay. Okay, so let's call these antichains simple with respect to U. So what we have just shown basically is that if A is simple, if every maximal antichain A is simple, then VB mod U is contained in the intersection of the MAs. Okay, and in general, of course, VB mod U is contained in the intersection of all the MAs for which A is simple. Okay. For the other direction, we unfortunately need a little more, and that is that there is a small generating system of maximal antichains. So let's call a skeleton a set of maximal antichains such that that system is directed under refinement. I want the pointwise image of A to be an element of VB mod U, and I want it to generate V check U. So V check U is the set of JFF of B sub A's where A is from this system, from this skeleton. So I only need the B sub A's as generators. So in a way, what I'm saying here is that I don't need many generators, so that I get that J image A is an element of VB mod U. Okay, and it turns out that getting J pointwise image of A into VB mod U means just that VB mod U has to be delta closed, where delta is the cardinality of A. Okay. Okay, so if there is a simple skeleton, then we get identity or equality here. And if so here I intersected only the elements of the skeleton, but if there is a skeleton and every maximal anti-train is simple, then we get the desired identity. Yeah. So okay, so this you can run through the proof. Basically, try to imitate what you would argue in the case of Prikry forcing. So let me just skip that. Okay, so but it's kind of abstract, right? So the question is, when are the anti-chains simple? So I just made the assumptions I needed to be able to prove the theorem. So here is a criterion. So first, so what does it mean for G sub A to be in M sub A? Well, there has to be a function that represents this G sub A, and you can write down what that function has to satisfy. So right, the function, let's call it vector G, is G sub A little a for A in A is a function, right? And we want the equivalence class modulo U sub A to be G sub A. And you can just calculate and see what that means. It means that for every pressing down function f from A into the Boolean algebra, that means that f of little a is always below A. So for every such function, the supremum of the f of a's is in U if and only if the supremum of the a's such that f of little a is in G sub little a is in U. Okay, so this is equivalent. And the question is, where would these come from? Okay, so I'm almost out of time. So just a few words about this. So remember, we got this U by pulling back G, right? This was how we got the ultrafilter on the Boolean algebra. If you look at it, as far as Prikry conditions are concerned, so just in the forcing, not in the Boolean algebra, it's exactly the 0, x conditions. They don't have anything in their first coordinate, because when you pull back G in the first coordinate, you only have critical points, so they are never in the range. So when you pull back, you get these guys, 0, x. And and this U bar, this generates an ultrafilter on B. And the reason for this is the Prikry property, because you can decide every statement without increasing the first coordinate. In particular, you can decide the statement B check is an element of G dot, right? So by the Prikry property, these guys generate ultrafilters, and they do this below. It didn't matter that I worked below the empty set here. I could do this below any condition. So we get, in a canonical way, a system G sub P of ultrafilters. Okay, and so if I work with these, then basically what happens is we can define a strong version of the Prikry property, which ensures that we have a system which represents G sub A for every maximal anti-chain A. So a strengthening of the Prikry property will give you that G sub A is always in MA, and hence that this Bukowski-Delannoy identity holds as long as there is a small skeleton. Okay, so as long as you don't need too many generators. Okay, sorry for going over time. Okay, yeah, sorry again.